goes. Factoring. The next piece we're going to look at is factoring each expression. So we want to factor secant squared of x minus 1. Now it might be a little odd trying to factor this or seeing how this factors. So one thing we can do is using something called U substitution. U substitution. And the way we use U substitution is we take U and set it equal to part of our expression. And here we're just going to set U is equal to secant of x. We're going to find U to be secant of x. Now for the equation, really what we're saying is that we have this secant term. Secant of x is being squared, is being multiplied by itself minus 1. So when we apply this U substitution, we're really just going to replace secant with U, saying that we have U squared minus 1. Now we might not be as familiar or see how we can factor secant squared minus 1, but U squared minus 1 is a difference of perfect squares. And really, secant squared minus 1 is a difference of perfect squares. It's our a squared minus b squared. Factors 2, a plus b times a minus b. And for us here, U squared minus 1 would be U minus 1 times U plus 1. Questions on this here? Now at this point here, we would need to plug secant back in because we're not really factoring U squared minus 1. It was secant squared minus 1. So it really just tells us that secant of x minus 1 times secant of x plus 1 is this factored. So we just use the U substitution step as a in-between to get to where we want. Questions on this here? No, because we could have gone just from secant squared minus 1 to secant of x minus 1 times secant of x plus 1. Use an extra step so we can easily, or see it easier, how it factors. Questions on this here? We're ready for the next one. 4 tangent squared of theta plus tangent of theta minus 3. So we need to factor this. Now we could use U substitution, or we can do our normal factoring. So when we factor this, the first thing we need to be looking for is a greatest common factor. Something, a term or number that will go into all 3 terms. Unfortunately, there is not one. There's not a number that goes into 4, 1, or 3, and we don't have tangent across all 3. So we move to our 2 sets of parentheses with 3 spaces. Our third step is the sign. If the third term is positive, the signs are the same and match the sign of the middle term. If the third term is negative, the signs are opposite. So one's going to be positive, one is going to be negative. At this point here, we need to find the factors of the first and third terms. Well, like with variables, the only way we can get tangent squared is, well, tangent times tangent. So in the first spots, we'll have tangent of theta and tangent of theta. We have to have one in each, and I do not know why I wrote it so small. We've got tangent of theta tangent of theta. Now the factors of 4 are 1 and 4 or 2 and 2. Which one do we want to try first? 1 and 4? I'll put the 4 here. Factors of 3 are 1 and 3. So where do we want to put the 3? And where do we want to put the 1? 1 or 3? 3, 1. And the last thing we need to do is check and make sure we got the correct setup. 4 tangent times -1 is -4 tangent of theta. And our 3 times tangent of theta is plus 3 tangent of theta. And -4 tangent of theta plus 3 tangent of theta is negative tangent of theta. So we need to switch the signs. If we get the correct term but wrong sign, we flip the signs. Because this time now we get positive 4 tangent of theta minus 3 tangent of theta, leaving us with just tangent of theta. So we don't necessarily have to use U substitution, because we can do this here without it and get the same thing. Questions on this here? Are you ready for the next one? 1 minus cosine squared, and we're wanting to factor it. Well, this here is a difference of perfect squares. So our difference of perfect squares was defined as a squared minus b squared is equal to a plus b and a minus b. Well, our first term, our value of a, well, would be 1, because it squared is 1. And the other term would be what? Cosine of theta, yep. Because really a, in our case, would be 1, b would be cosine. So we get 1 plus cosine and 1 minus cosine. Difference of perfect squares. Yeah, we're just out the u. Because the u substitution is nice if we're not really able to see what we're looking at or trying to factor. Because we could have factored or set u equal to cosine of theta, which would have given us 1 minus u squared. And gone from there. Questions on this here? How do we feel about this so far? Does it feel very similar to solving or factoring quadratics? It is. It's just instead of having x, we have cosine or sine. And they work the exact same way. Now let's look at this one here. 2 cosecant squared of theta minus cosecant of theta plus 6. Is there a greatest common factor? No. So we'll go to 2 sets of parentheses with 3 spaces. If the third term is positive, the signs are the same and match the sign of the middle term. If the third term is negative, the signs are opposite. Well, here the third term is positive, so the signs are the same and match sign of the middle term. So we have negative and negative. We're looking at the factors of the first term. Well, we're going to have cosecant of theta in both, because it's cosecant squared. Those are the factors of cosecant squared. Factors of 2 are, well, 1 and 2, so we need to put the 2 somewhere. Doesn't really matter which one do we want to put it with. First one or second one? First one. Now we need to find the factors of our third term, factors of 6. 1 and 6, 2 and 3. Which one do we want to try first? 2 and 3. Which 2 or 3 goes here? 3, 2. And if we check this, 2 cosine of theta times -2 would be -4, not cosine, cosecant of theta. -3 times cosecant of theta would be -3 cosecant of theta, giving us -7 cosecant of theta. Is that the middle term we wanted? So these here are our correct factors. Questions on any of this here? We're ready for the next one. Cosecant squared of theta minus cotangent of theta minus 3. There's an issue we have with this one. Our terms are not the same. Because I either need it all in terms of cosecant or all in terms of cotangent. Now, we did have one of our Pythagorean identities. Cotangent of theta, square of theta, plus 1 is equal to cosecant squared of theta. So this is one of our 3 Pythagorean identities, and we do have cosecant squared given in our equation, yes? So what I can do to get this into a factorable form is replace cosecant squared of theta with cotangent squared of theta plus 1. Because if we're going to factor, we need it all in terms of cotangents, all in terms of sine, cosine, tangent, secant, cosecant, because we all need it to be the same. For quadratics, this is essentially we had y squared minus x. We have 2 different terms. They're not the same. Does that make sense? So, You're good? Yeah, no, cotangent squared plus 1 equals cosecant squared is one of our Pythagorean identities. There's a good likelihood that if we're needing to replace something or use a formula, and especially if it's squared, we're going to be using one of those Pythagorean. If we're trying to reduce something, the Pythagoreans, those 3 formulas, are very helpful and they're very useful. Those are the main ones we'll be using a lot of times. Does that make sense how we got there? Yes. So I'd be focusing on those, especially if you see a square, we're trying to rewrite something, trying to get something in the same terms. We normally go there. Now at this point, we don't need the parentheses. And we can combine like terms. Because our 1 and negative 3 are the only like terms. So it tells us that we have cotangent squared minus cotangent minus 2. And since we now have this all in terms of cotangent, we can factor. If the third term is positive, the signs are the same and match the sign of the middle term. If the third term is negative, our signs are opposite. Here, the third term is negative, so we're going to have plus and minus. The only factors for cotangent squared are, well, cotangent and cotangent. Only ones we got. Factors of 2 are 1 and 2. Where do we want to put the 1? 1 with the positive, 2 with the negative. If we check, cotangent times negative 2 is negative 2 cotangent. 1 times tangent is positive cotangent, which does give us a negative cotangent of theta. So these here are our correct factors. Questions on this here? The fridge. Yeah. And I think it was like that down in Mr. Cherry's room too. I think it's getting there. It's almost the same as the compressor in that closet over there too. Because every now and then there is a compressor that kicks on for the sprinkler system. But it's I've completely tuned the air compressor out at this point, or the compressor in that closet. It will startle me if I have that closet open or I'm in that closet when it kicks on. All right. Let's look at this next one. So, looking at this one here, what do we need to do first? We need them to be the same terms. Now, it does work out that tangent squared plus 1 is equal to secant. Now, is there anything in front of secant squared? 1, because there's no negative sign, there's no other number in front of secant squared. So we could write it in as tangent squared plus 1 to replace our secant squared. But is there anything we're going to have to distribute through these parentheses to our tangent squared plus 1? Is there a number or something in front of secant that's having to be applied to it? No. So we don't necessarily need the parentheses. We can put them. It's not wrong to put them, but we're going to end up dropping them and they're going to go away. And what that's going to leave us with is tangent squared of theta plus 3 tangent of theta plus 2. Two sets of parentheses with 3 spaces. Since our third term is positive, the signs are the same and match the sign of the middle term. Plus and plus. Well, there's only one set of factors for tangent squared, and that's tangent of theta and tangent of theta. Only factors of 2 are 1 and 2. And if we do check it, we do find that tangent of theta plus 1 times tangent of theta plus 2 is the correct factorization for this here. Questions on this here? We're ready for the next one. Simplify each expression. We want to simplify this as far as we possibly can. Yeah, I don't know why it decided not to print these. So we want to simplify this down as far as we can. Now, these here, and especially on the homework, are going to be pretty much simplify the following expressions as simple as possible. The answers may vary. And there are some ways that the answers can vary from one to the next. But the best way I find with some of these here is for especially this one, let's get it in terms of sine and cosine. Because sine of t is already in terms of sine. Plus, if I rewrote cotangent in terms of sine and cosine, what is cotangent the same as? What over what? Cosine over sine. Also, it is on your reference sheet up at the top. Tangent, sine over cosine. Cotangent's cosine over sine. And that kind of follows along because tangent is the flip of cotangent and cotangent is the flip of tangent, or they're the reverse of each other. Okay. We can multiply these here. And when we multiply cosine of t by our cosine over sine, and that should be t, not theta, we multiply with the cosine on top because it's cosine of t. Outside is really just cosine of t over 1. So for this here, we get cosine squared of t over sine of t. Questions on this so far? It's kind of gotten a little bit simpler, but not at the same time. Because now we have square terms, so we do have two terms. Last thing we're going to need to do is add these two together. For me to be able to add a term and a fractional term, or to add two fractional terms, we need the denominators to be the same. Well, our main denominator for this is what? Sine of t, yes? So I need the other one to have a denominator of sine of t. And to do that, well, our first one does have a denominator, but it's 1. So to get it to have sine of t, I've got to multiply top and bottom by sine of t. And doing that will give me a denominator of sine of t. And the numerator, sine of t times sine of t, is sine squared of t. Questions on this here? Are we in the realm of this makes sense and doesn't make sense at the same time? Because we're really trying to get this condensed down. If we can get it to be a single term, if possible, that's our goal. We use sine and cosine because that's a little bit easier to work with, because we can match it up, sine and cosine. Now at this point, the reason we're doing this adding, because if I can get it to be a single term, that makes things better. And if there's any of our Pythagorean identities that show up, we're going to utilize them. Because now we can add. Since the denominators are the same, we can add the numerators. So we get sine squared of t plus cosine squared of t over sine of t. Did one of our identities show up? Our Pythagorean. I think it's the first one listed, isn't it? For Pythagorean. Sine squared plus cosine is what? So what does that tell us about the top of this fraction? So this here is the same as 1 over 1 over sine of t. So can we say at this point this does look a little simpler than what we started with? Also at the top of our reference sheet are reciprocal and quotient functions. What is 1 over sine of t, or 1 over sine, the same as? Our cosecant of. So our sine of t plus cotangent times cosine is the exact same value as cosecant of t. Questions on this here? It's odd. I will say this. It's odd that this works the way it does. And would y'all say y'all feel like we're just manipulating these equations to get what we want? Yeah, and that's a lot of this. Questions on this here? And the biggest thing I would say, especially with trying these here and working with these, is that if you see something that you think works, go for it and start using these here. The Pythagorean identities are going to be especially helpful with these here, and getting these in terms of sine and cosine also help us out a good bit too. Because if we look at this one here, even though we're using x, doesn't make a big difference. Cotangent. is cosine of x over sine of x. Cosecant, CXC, well, that's the same as what? 1 over sine of x. I normally try to get them in terms of sine or cosine, especially if we're trying to simplify, reduce, because sometimes it's easier to see what we have. This one's still 1 over sine of x. Minus. If we multiply these two terms here, our cosine of x times cosine of x does give us cosine squared of x over sine of x. Denominators are the same, so we can do what? We can. So here we'll subtract since there's a subtraction in between them, so we'd have 1 minus cosine squared of x over sine of x. Cosine squared and 1. So we have cosine squared, yes? Really, if we're looking at these squares and trying to reduce, simplify, we're going back to Pythagorean. Now, unlike the last one, it was nice. Cosine squared plus sine squared equals 1. We just replace it as 1. Yes? So this is Pythagorean identity. So the first one in that list. This. Yeah. Oh, I flipped them. Wait, no, I didn't. Yeah. So that's one of our theorems. The sine squared plus cosine squared. Where did I get the 1 minus? Oh, no, this is just the theorem. So that's just the theorem. I just wrote it out there just as a reference point. We didn't change anything. Because at this point, there's different ways we can use this theorem in this formula. Because one of them, as we saw the other day, is I can just replace the 1 in the theorem with sine squared plus cosine squared and simplify down. Another way we can do this is take this and solve it for cosine. So we would subtract sine squared, and that's just a poorly written sign, which would tell us that cosine is equal to 1 minus sine squared. Do we understand how we got to the 1 in red? Because we just minus sine squared and got there. Now, if I had minus cosine squared, we would have gotten this form. Does it make sense how we got the 1 in red, 1 in blue? Yes, we're just manipulating it. So, again, as I said, there's more than one way, especially to get to the answer. We could plug in the 1 as sine squared plus cosine squared. I could plug cosine squared in, replace cosine with 1 minus sine squared. Or hey, last one we do have 1 minus cosine squared, yes? If I replace it with sine squared, we get sine squared of theta over sine of theta, which is, and no matter which one of those three that I mentioned, we will get to the same place. But it's picking one that you see, whichever one you see first, whichever one you're just naturally are drawn to or go to, do it and do it first. We'll finish this tomorrow.